Okay. All right. Just letting you know, I did Newton's second law in yellow. Like, it doesn't really matter, but I'm just telling you because some people were like, what did you do? So there it is. Okay. From the top, we used mass and we used acceleration already. So I'm trying to just stick with those colors if you're wondering, okay? So it says the acceleration, that was blue, of an object depends on the mass, that was purple, and how much force is applied. We're going to use green for that. Now, if you go to the picture right there, the first picture we see with the vehicle and the little camper, we are now going to label that picture with the words acceleration, mass, and force. Okay? So in this picture right here, what would be each thing? Like, how do we label it? Acceleration is not the car. Where am I putting the word acceleration? Let's do acceleration last. How about that? Do the other two, and it'll make a little bit more sense. Where's the force go? Hold up. Where is this going to get its newtons? From the car. The car is the force. What is the mass? The camper. Who doesn't understand? Okay, and then what's our acceleration going to be? Which way? Does that make sense? Y'all kind of scaring me. All right. Same three words in this picture. Very good. Okay, I'm going to have to do this and do this. So the force is here and here. Force. Green. You're standing right there. And if you would have been in here, then you would know. Okay, what else? The fish is the mass.
The acceleration is going up.
Yes. Okay. Who said what?
When you're doing force, do you have to tell how the force is working acting on it, or can you put force? Like, do you have to?
Like, do I have to draw this?
No, do you have to say how the force is acting on it?
Right now, no.
But on a future reference?
Maybe.
Okay.
Okay? This one.
The wind is the force.
Wrong color.
The mass is the flower.
Acceleration is what? Toward the right. I mean, I don't know. It could be a question in words where you're looking at a diagram and you have to, like, it's multiple choice with all kind of words. You know what I'm saying? So you've just got to be able to look at a picture of something and be able to break it all down. Identify all the stuff that could be there. Okay? All right, this one.
The force is the guy holding them up, because he's like pulling them up.
Only that?
Pushing them, and the one and he's pushing down on the.
This is like a person who's shopping and has all their boxes, their gifts?
Because Rachel said that down.
No.
She's pushing the boxes up.
She is pushing the boxes up, but
That way they don't fall.
but what else is holding her up?
Her feet.
Her legs. She needs a force from her legs and her hands to hold those boxes up. Does that make sense?
Yeah. So it's like, if the legs,
Because if the legs aren't there,
then she was like, she would fall.
yeah, she would just fall. Yeah, great. Her hands are holding them, but she's standing right now and holding.
Oh.
Okay? Okay, come on. What next?
That's the thing.
Acceleration is just going to be, well, I've been putting my acceleration over here because her feet are kind of turned that way. Like, whenever she turns and walks away,
She's accelerating.
that's her acceleration. You know, her going on to the car or going on to another store or whatever, that's her acceleration.
Not even.
Okay, so this is the whole second law right there. That explains every part of it.
Wow.
That's simple. This is my thing about the second law. No one should miss second law because it is so common sense. So common sense. Okay, let's take this for example. If I increase my force, if my force would go up, or it could be you that you're holding it and you blow on it, okay? If that goes up, what else happens? The acceleration goes up. Y'all, it would like fly away faster and farther. That is common sense. If I pull this harder, what's that going to do? Okay, and I can also say, what if I catch a bigger fish? Let's do this. My mass goes up. And then, so what do I have to have? More force. No, I have to have more force to accelerate at the same amount. If the mass goes up, my force has to go up to equal that A. It is a formula. But it's a common sense formula. What the heck if you have a bigger fish on the end and you pull the same amount that you just did with him? What are you going to do? Nothing. Your fish is going to lose. Yeah, you're going to lose your fish. He's going to jump off. It's so common sense. The other thing is, in most of the questions about the second law, they talk about objects that are not the same size. Because that's different mass. So you should not get Law 2 wrong. Yes, we might struggle a little bit more with 1 and 3, but I'm going to help you be able to break that down. Law 2 is common sense. Okay? The back. Okay, I did use green for force, a push or pull on an object. It's also the strength or energy that moves an object. We've talked about force already. Okay, y'all can color all that later. Let's look at this first picture. Where is the force of friction in this picture?
The box sliding against the ground. No, there's friction between.
Friction happens between two surfaces, yes. So, I'm going to draw it. like right there. Yep, the hills and valleys. That's friction. Yep. If this is my push, what happens?
Your pool is.
I don't have a pull. Okay, so we don't understand. Y'all, vectors, you have to look at the size and the direction of the force. So I have a vector right here, and I have a vector right here. It's not going to move. Who doesn't understand? Does this cancel out with that? So the friction is greater. He's holding it. Duh. Sorry, resist motion. You have to use your brain. Yeah, a little. Gravity. Yep. And this would be like the earth. Right? Okay, now this is our first little touch on magnetism. Is there anything that y'all could tell about? Do y'all know anything about this?
Yeah.
What?
If opposite ends attract and the same ends repel.
Okay, so what would this one be?
Those two would attract. Those two, yeah, they would attract.
Okay, and we're going to draw it. Weren't you here yesterday? Put it down. Go write it on your loose leaf paper. We're going to draw it like this.
I've seen this before.
Right? And what did y'all tell me the bottom two are?
They repel.
Yes. I wouldn't let you use the wrong ones.
So I learned that the magnet was
Force. Yeah, that's what we're learning. Force.
I've seen this somewhere else. Just not, like the whole.
Oh, we're going to do, yeah, we're going to do way more with this, but, okay. The third law. The third law, I did that one in orange, y'all. So, I mean, if you want to follow that color pattern I've been using, you can. If you don't, I don't care. More power to you, whatever. But I did that in orange, okay? Forces always occur in equal and opposite pairs. Okay, that's what the third law says. Actually, it's way more detailed, but we'll go with this. So I want to draw an arrow right here. And I want to draw another one right here. And I want them to be the same size, which, because I'm showing you they're equal, but he's to the left and he's to the right, so they are opposite. Equal and opposite. Okay? Does that make sense? Anybody have a question? All right, so let's break this one down first. How does this work? That's a hammer and a nail. Okay, the hammer pushes the nail down on the nail. So we're going to say this is the action. Hammer pushes nail. Okay? It's not normal. It's equal. That's not the normal force. The hammer pushes the nail down, and the nail pushes back, in the opposite direction. Notice those arrows. Yep. Why, what? Oh, it always is. It doesn't matter what nail you're using. It's always going to be the force that the hammer puts on the nail puts back on the hammer. That's what Newton's law is telling you. The hammer pushes the nail, and the nail pushes back. Yep.
I actually used that excuse yesterday. Really? Did it work? Yeah. It worked. My mom didn't
Are we okay with this? See, because one object puts a force on a second one, and the second one puts an equal force in the opposite direction. That maybe it does. Okay, you know how whenever you use the hammer, you can actually feel it make the contact with the nail? That's the nail pushing it back. Okay? Yeah, I know. Okay, so you probably didn't imagine that walking is Newton's third law. Yes. So, how this actually works is your foot pushes back. You didn't know that. Okay, look. I don't know how I can show this on that video, but this is our foot. You see my hand? We walk heel-toe. Heel-toe. So if I'm doing heel-toe, look, I'm pushing that way. And when I push the ground that way, it pushes me forward. So when we draw this other arrow, it needs to be the same size. Oh, I don't know if mine are, but there you go. Yeah. Okay? What about this one? The paddle pushes the water back. Paddle pushes water. Water pushes back, so where does the canoe go? Forward. Are we cool? Everybody understands the third law? Okay, so the one thing I want to make sure of whenever you have to draw for the third law, guys, for the third law, when you have to draw, the arrows are the same size. It's the only one where the arrows are the same size. Does that make sense? Okay? And look, it always really talks about opposite direction. So when you read examples, you got to look at your key words. Okay? Okay, last thing, momentum. Momentum. I did momentum in blue. Blue will work. The or strength. It's how much punch you're going to pack. Like when they say, man, he packs a punch. Like it's how... It's the one yesterday where I said, I'd rather be hit by the car than the big bulldozer thing. Yeah. Yeah. During collision, the force of the cars causes a change in momentum. Okay? But the total momentum before the crash, however much momentum you have before a crash, It's the exact same at the end. They just trade it off. That's why if a big old 18-wheeler hits you, okay, he trades his momentum to the car. If the car ends, now the car hits him back, because the third law says that, right? Okay, so that's how he gets smashed too, right? Does that make sense? But it's not too bad because the car took a lot of it and he doesn't transfer as much back. But it's there, and it can also turn into friction. Oh, yeah. Yeah, no machine is 100% efficient. You always lose something to friction. Yeah, I mean, two things are surfaces touching. So what might happen if car 1 was stopped and car 2 hit it going full speed? How would the momentum and motion of the car be impacted?
Well, the car that he hit would go forward.
Okay, so car 1 would gain what? Okay, gain momentum and accelerate / move forward. Right? Does that make sense? Don't think of accelerate like you put the foot on the gas. Okay. I mean, but he's gonna go from 0 to a new speed, so that is acceleration. The speed's going up. Okay, what about car 2?
Car 2, he would stop. He would keep his momentum.
Nope. He loses his momentum. And slow down. Eventually, yes, friction is going to stop him, which is not the same. Momentum's not friction, okay?
Would he slow down / decelerate?
Well, I kind of think that part of him would move back.
So yeah, because
Like, he's going to hit him,
and the car's
but he's going to hit him back. So I want to say roll back. Does that make sense? Because he's going to end up having some motion that goes the other way. Yeah. Okay? That makes sense?
Yeah.
Now, what about the total momentum? Cool? We're doing okay on time, I think. Yeah, we're doing good. Can I move it? No? Okay. What? What experiment? Oh, the one out? Oh, we're going to get to that. Hang on. I want to do this one first.
What about those?
That's for tomorrow. I started getting this stuff ready for tomorrow. Okay. So I can take these little things right here. They're fans. Okay? And if the fan is not on,
You get no air.
Okay, so first law is an object at rest stays at rest until an unbalanced force acts on it. Okay, so if I turn the fan on and click play, I have a force that makes me accelerate. Okay, and it took me 5 seconds to go 10 meters. Now, right here is my air. My air is pointing that way. Which way did the cart go? So, which law is that? Nope. Third. Who doesn't understand? Who's in the middle? Okay, you ready? Break it down. This is object 1. It's pushing on the air. Yeah, it's pushing on the air, okay? When it pushes this way to the left, the air, okay, it'll come back on. The air pushes back in the opposite direction. Okay? If I take another fan and turn it on, what do I have more of? Nope. Force. Yeah, but it's just a little bit, there's going to be more, I'm going to get more from the force than the mass. The mass is, you are right, I'm going to add a little bit of mass, but the force is going to make a bigger difference. What do we expect should happen? Goes faster. Okay, let's test. 4.3 seconds. So it went faster. Okay? So if we take it and add the third fan. Even more force, so acceleration should go up. 4.1. Does that make sense? Okay. That is the second law. Acceleration depends on the mass of the object and how much force is applied. If I take this little mass right here and add it to the cart, what's going to happen to my acceleration? It's going to slow down. It takes us 5 seconds. That's equal to the one fan. Well, not necessarily. There could be a relationship between that, but I don't know if it. I haven't sat and calculated it all. I don't know if it does. I don't think it's equal to anything. But do you get the concept? Does everybody understand? Okay, let me just show you this real quick. See that? What should happen? Which way should it go? Left or right? Okay, it should go to the right, but is it going to go the same as it just did? What's going to happen? Slower? Why? What is he providing?
He's providing that way. He's providing negative.
Friction. Air resistance is friction. Look at him. Look at him.
But what if you make it equal? Oh, no.
Yes.
If you made it equal, would it be at rest? Like 2 fans going this way?
Ah.
Would it be equal? It wouldn't do anything.
Balanced forces. It doesn't matter. Balanced forces. Look, watch.
Okay, now it's going somewhere. Wait,
But then he keeps on going because they're at a constant speed. I had to give him a little bit of force to start off, but then when I switched him back around, constant speed in a straight line because I made the forces equal. No. Nope. Okay, let's do the other experiment. Let me stop this.